then screen share on the other side. There we go. Alrighty. Cool. So YouTube should be starting in, oh, right there. Okay, it just pops up. So we got everything up and running. And I think I'm gonna turn off my webcam today, because I might need the entire area to explain things. So this way I can also zoom in a little bit, because otherwise the font can be a little bit small, and when people are just watching it on a smaller screen. Alright, cool. I'm just checking the text channel and make sure that I'm not missing anything. We still got a minute to go, so I'll just let people to kind of come back here. Alright, so I'm not sure whether I have asked this class or not, whether you guys prefer your classes to be fully online asynchronous, fully online synchronous, or face-to-face. So you can express your preferences, either by direct message if you want to just answer to me, or you can also post it in today's channel if you want to. I think that really depends on who is teaching, right? Because some teachers are probably very good at asynchronous type of teaching. I'm just not one of those people. So what is the version this class is in? So this class is in, right now it's in 100% synchronous mode, and that's why we have synchronous lecture. I'm here, you're here, we're all here in real time, but it's still not really quite reproducing the face-to-face environment. And then face-to-face, the labs would also be face-to-face, which means you guys can kind of chat with each other, like the guy who's sitting next to you, and you can look at each other's screen, which I don't mind, when you guys are doing the lab, as long as you're not copying the answer. So if you're showing, the other person like an experiment that you have set up with, say, Logisim, and go like, okay, I'm doing this, but I'm not quite sure why this output is like this, and so on, that's actually very beneficial. It's harder, much harder to do that using a fully online environment, especially when you're working with Zoom. Discord makes it very easy. I mean, you guys can DM each other and share screens and do all kinds of stuff, even better than a face-to-face environment. Yeah, it depends on the class, and I think it really depends on the instructor. If I were to teach this class asynchronous, I would be the first one missing in action. Yes, I know myself really well, so I have to teach the class in synchronous mode, because that gives me structure. So that's that. Oh, okay. Yeah, I think face to face is even better, in many ways, because well, okay, it depends. For some people, if some people are more willing to type out their questions instead of raising their hand and try to ask questions in class, so for those people, I mean, synchronous online may be better. But even if I go back to campus, I'm gonna use Discord too. So people who are actually sitting physically in class can still use their phone or their laptop computer and text me in Discord, and I'll just be looking at the other side of the screen and go like, oh, okay, somebody just asked a question. So I don't see why that cannot happen. With a full face-to-face class, is people can still use an electronic means to type a question in the text channel. That's kind of funny. If you think about it, it sounds really funny, but it's not. I mean, it really helps certain people who may not feel comfortable asking questions to really also ask questions, but not just not in a audio way. So that's that. Yeah, I think so too. Alrighty, so we are gonna get into exam two from the last semester. Oh, yeah. So the streaming part, the quality of the audio and video, that really has to do with how they set things up. The school has enough bandwidth, so it's never really a bandwidth issue, because I have always streamed my classes, even when I was teaching face to face before the pandemic. I have always been streaming it to YouTube, just for recording purposes, and I never had a problem with the quality of both the video and also the audio portion. Um, And the new STEM building actually is specifically designed to have high bandwidth, Wi-Fi as well. So it really should not be an issue. It's just some people may not know how to set up the codec, and they might be setting up the codec to use an extremely low bandwidth, and that can be a problem. Alrighty, so let's move on and talk about question number 1. And if people are looking at question number 1 and go like, we have never seen this circuit before, those people would have been correct. So this is what I do sometimes is I would just kind of go like, there's another way to do this circuit. I'm going to use the other way, because the idea is still the same. I mean, how you track down, what changes is going to cause what to happen. That part doesn't change. Okay, what does change is you cannot assume this is one of the circuits you have seen and just kind of repeat the analysis that we have done in class. So this kind of forces people to really look at the circuit and find out what this circuit is going to do. All right, so first thing first, we are going to set up a template, because that's something that I have been struggling with, not you but me, is how do we represent the state of the entire circuit here. So we're going to have A. So A is easy. A is just a pin, so that means A just has a single port, so we are not too concerned about A, B, or C. So A, B, and C, they only have a port, which are inputs. P and Q are kind of the same thing. They are output pins and they only have a port, so they don't really do anything actively. There's no computation going on. There's no propagational delay involved with input pins and output pins. So P dot port and then Q dot port. So those are non-issues. And then we have X and Y. Okay, those are AND gates. So as a 2-input AND gate, we got a few things. So X has an output. X also has 2 inputs, right? So I'm going to use the array notation, to refer to the first and the second inputs. But since when we use arrays in C and C++, it is 0 oriented, and that's what I'm keeping here. And the same with Y. Y has in 0, Y has in 1, and to be consistent with the other one, I'm going to put Y dot out as the first thing. So the output is the first thing that I would list. And you can see how this list gets a little bit long, it gets a little lengthy. And then we got V and W, those are the NOR gates. Okay, they're the NOR gates. And let me see if you guys remember when we talked about the NOR gate, because we specifically talked about the NOR gate, I think just on Tuesday. So you guys can type in the text channel, in what context did we talk about the NOR gate? As I try to finish typing all of this stuff here, because once I have the template, the rest would be fairly easy to do. And in the exam, depending on how this works out today, I might even give you this template here so you don't have to type out this whole thing. Yep, exactly. So Bernard is correct. It's for computing the Z flag. So the Z flag is the NOR of all the bits of the output of the ALU. So in other words, it just looks at the output. If the output is indeed a 0, which means all 8 bits are zeros, then the Z flag is going to be a 1. That's what the NOR gate was doing inside the ALU. So Bernard was mostly correct. Okay, he just kind of missing that one little detail of which flag it is for. Alrighty, so I got the template in, so now we can go ahead and apply the template. So initially everything is unknown. Okay, so what we need to do is to copy and paste this entire thing under here. Okay, so I'm going to put it under explain your answer in phases. A phase starts with da 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 da. Okay, so alright, so I'm just going to put it immediately under the input pin states. So this way I can now say, okay, A dot port is a 0. It's a change from not knowing what it was from before. So all of these are just kind of could be copied. Alright, so now this is going to be a little bit of a problem. I have a solution to this. So let me just kind of use this solution. I'm using a little screenshot tool that I have for screenshotting just a portion of the screen. I think you can see that too. Yeah, you can see that. And instead of putting it into the clipboard, I'm going to open it with FEH. FEH is the name of the program. Don't ask me why it's called FEH. Okay, there we go. And we can just go ahead and make it always on top. There we go. Alright, so this way I can scroll the text window and this will always be here, and it's easier to refer to the circuit like this. And I'm trying to move this up as much as I can without interfering with the part where I'll be typing. So these are little tricks that you can also do because you're going to be using a computer to to answer the questions, so you can basically use the same kind of trick here. And having your browser pointed to this document is helpful as well, because then you can stay on a certain part when I'm scrolling around and typing stuff. Alrighty, so the first thing is the first phase is to look at the node connectivity so that we can find out which input is connected to A as an input pin, which input is connected to B, and which input is connected to C. So those are all illustrated here. So the input of the AND gate and the NOR gate, I just count from top to bottom. So the top one is input 0 and then the bottom one is input 1. So that way I can just go ahead and say by connectivity, we know x.in0 is the same as the A port, which is 0. In.1 or x.in1 is B, which is also at 0. And then y.in0 is B, which has a value of 0. And then y.in1 has a value of 1. And that's it. Okay, so this concludes what I can figure out just by connectivity. So right now I'm not even bothering to try to figure out what an AND gate is going to do. All I'm trying to do is to figure out, okay, now that we know the port A as an input pin has a value of 0, who else is going to get the 0 because they are connected by nodes. So this is the node connectivity phase. And once we have that, we can now move on. So obviously this is taking up quite a bit of space. So if you want to save some space, you can probably use a table to do it. So the next one is propagational delay or propagational yeah, so it's 1 PD after this. And then the one before is node connectivity. So I'm just going to use NC to stand for node connectivity. And now we are looking at a propagation to determine how the outputs are going to be affected by the input. Alright, so we got questions in the text channel. Do we need to write out all of the previous parts, all the various parts or values at the node connectivity stage? I just do that because I'm going to use the same template over and over again. In this test, having a really long answer is not a concern because we are not using paper. So you can use it, you can basically make it as long as you want. And this way, I am not going to miss anything. That is the thing, is I'm not going to miss anything because I got everything on this list. So that's going to be useful. All right, it's a little redundant. It may be redundant, but this way I'm not gonna miss anything. I think that's important to me. Okay, yeah, whether it's important to you is up to you. All right. So because we basically specify an input of x and we specify some inputs of y, so that means those two need to be analyzed to find out whether their output can be determined, and if so, what they are going to be. So the first one is x.out. And we want to see if we can now tell what output x is going to be, what x is going to be outputting. And because we know both inputs of x are zeros, so that means we know the output of x is going to be a 0. And I am going to highlight this, okay, because now I can see the change. Okay, one of the one component x has a determined output now. And the same thing for y. Okay, so y also has an output of 0 because y is also an AND gate, and both inputs are, excuse me, at least one input is a 0, so the output of y also has to be a 0. So the both phase is helpful because now I know, in the node connectivity phase, I need to track down what x dot out and y dot out are connected to. So that's basically how I can track okay, this change is propagating to those components, and then those components work a little bit, takes a little bit of time, and then their components, their output is going to output to those other components, and so on. So that's why it is important. Alright, so we'll go ahead and copy and paste this over here. And okay, so that's my fault, because I should have kind of write down NC first for node connectivity. So based on node connectivity, we know that we have to track down x dot out, and x dot out goes to v dot in 1. Okay, so v dot in 1 is going to get a 0, and I'm going to say because of x dot out. And then the other one, y, is going to w dot in 0. So w dot in 0 is also getting a 0 because of y dot out. Okay, so you can use abbreviation like BC or B/C for because this way you don't have to type too much stuff. So the important part here is now I have to kind of highlight v dot out. So before I do that, I am going to change these so that they don't have any highlights, because I don't want to look at all the things that are bold faces, and they really should not be bold faces anymore, because we just took care of that propagation. So there's a tool you can get rid of formatting. I'm just looking for that tool right now. I don't think it's that one. I think it's under the dot 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 maybe. Yep. Alright, so under the dot 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 you can find this tool that has a cross or a slash across T. That's for deleting the formatting. So anything that was bold faces is no longer bold faced anymore. So instead, I'm going to have the bold face V as a component, because one of the input is now determined. So I'm going to boldface it, and same thing with W, because one of the inputs is now determined. So I have to boldface it. Alright, so let's go ahead and continue, and this time I remember my mistake from last time. Okay, so I'm going to do a PD here for propagational delay, and after a certain propagational delay, just copy and paste. So I think this is a whole lot easier than you having to type the entire thing, because when we copy and paste, it also preserves the boldface. So that means now we know what component we have to do some analysis and see if we can now tell what the output is going to be. Alright, so let's check it out. Okay, so we can see v dot out is going to be one of the things that we might want to say, okay, can we determine the output of v dot out now? And the answer is no, because we only know one of the input pins. Now this is not a NAND gate, this is a NOR gate. So with a NOR gate, if only one input is known to be a 0 but the other one is not known at all, then you cannot really say anything. You just have to say, not really sure about the output right now. It's just something, but it's not known. Okay, so in that case, I'm going to put an equal to question mark here, because one input is a 0. The output cannot be determined. And as it turns out, the same argument can also be applied to W. So I'm just gonna do the lazy thing here, right? So we copy and paste it, because W also has an output. One of the input is now known, but we still cannot determine the output of W, because it really depends on what the other pin is saying. Because if the other pin is also a 0, then the output of W is going to be a 1. On the other hand, if the other input is a 1, then the output of W is going to be a 0. So this part really has to do with the what gate we're dealing with and what kind of input we are seeing. Now, because it is unknown and it was unknown before, so that means we're done. Okay, the propagation of changes this is as far as we can get. Okay, we cannot get past this particular point. So I'm going to pause here and see if there are any questions about this process. Omer is typing, so we'll go ahead and I mean, it's good to kind of pause, occasionally because this is a little bit of stuff here. It's just that I changed the way I trace and track down the changes. All right, just to confirm, will we be able to get a similar template in the actual exam if there is a similar question? All right, so the thing is, even if I don't give you a template, you can look at the circuitry and find out, okay, here's an AND gate with 2 inputs, here's a NOR gate with 2 inputs. So you can construct the template on your own if it is not given to you. Yes, that's going to take up some extra time. So hopefully I remember that I said this and I'll give you the template. But if I don't, okay, it's not going to be too big of a deal to come up with the template because the template is really just based on what kind of pins are available to a specific component and just name them all. So there you go. Yeah, so the coming up with a template itself is not really time consuming, but using it can save you a lot of time because now it is much easier to keep track of, oh, what was the previous state? You don't have to look up, right? You can just kind of look at the current template or the current instance of the template. You can look at a template like a class, right? You're looking at an object, so all of these are basically instances of the template. Alright, next thing is, so if the output cannot be determined, it's alright to stop there and consider the problem solved. No, it's not exactly solved. It is simply meaning that we cannot move on any further with that single component. Now, as it turns out, both components that we need to track now, they both have an output of unknown, which is no change from before, and that's why we can stop. So it doesn't, so just because one component has an output of unknown doesn't mean you can stop there. So you kind of have to look at the reasoning why we can stop now. We can stop now only because both components, all of the components that we need to track, they both have no change. And because they have no change, then we can stop. That is the reason why we can stop at this point. All right, Chris is asking, besides AND or NOR, what other gates could we expect in this portion? Well, I mean, those are pretty much the only gates that exclusive OR. That's kind of those are the only gates that we have used. If you look at Logisim, and look under gates, right? So those the gates that we typically use are those. Yes, there's a negated exclusive OR gate. I don't really see us using it. So, and oh, okay, add one more to that list, a single NOT gate, okay, which looks like a triangle with a little bubble. Yeah, so that one, may also be used in the circuit. But for the most part, you can just kind of match up the symbol, in Logisim and click on it, in Logisim and find out what it is. All right, next question. Do we need to build changing parts? And they are still undefined like v.out. Should we bold? Well, the bold facing is going to help you to track what you need to look at next. So that's why I bold face things so that it makes it easier for me to keep track of, okay, that thing just changed, let's find out what else connects to it, and then we can make changes to those other things. So that's why I boldface things. So if you have a really good memory, better than mine, and you just go like, yeah, I can track all that stuff without using boldface or any formatting, more power to you. So let's see here. I cannot comment on whether you can expect an SR latch. Because I really have not come up with the questions for for this semester, because I'm still kind of busy grading exam 1. Yeah, so exam 1 takes a long time. This is going to take a long time to grade too, because I'm going to I'm going to track all of these changes, and when I grade this particular type of exam. So there's a lot of details to track, and so the better you format your answer, the shorter time I need to grade it, to basically look at all the details. Alrighty, but that's my job. So now we can move on to the next one, because this particular propagation change has come to a point where there are no additional changes. So this is the next stage, and guess what? We can just copy and paste and change one thing, and then continue with our analysis. All right, so copy and make sure that we paste at the right point here. All right, so the first thing is node connectivity. So we want to track changes due to node connectivity. And the one change, okay, the one thing that got changed is this 0 changing to a 1. So I am just going to highlight it with a boldface, and whatever was boldface before, I'm going to remove all that formatting, because I don't really need to change. I don't that's it's already taken care of, so they're no longer significant to me. So now I can just go ahead and remove the formatting for the rest. And now I can look at this and go like, okay, we are starting with pin B in this case, and we are trying to find out how it is going to affect other things, right? So so based on what I'm using here, I think I can turn the webcam back on, because I think I got room here to show my face. There we go. I mean, obviously showing my face is not going to help you understand the material, but that's partially one reason why I go for a fully synchronous class, is so that I can show my face. All right. One of these days, when deep fake, becomes reality, then I can change my face to some anime characters. That would be kind of funny. Alrighty. So moving on. Lesson. I have to stop myself from getting distracted, because I tend to get distracted myself. Alright, so we need to track, where is B connected to? So B connects to X in 1 and Y in 0. So now we can now go to those two pins and change them. So X in 1 is now changed to a 1, and I'm gonna boldface it, right? Because it just changed. And Y in 0 is also changed to a 1 now, so I'm gonna boldface that also. And this boldface is now not important, but I'm going to keep it here until I copy and paste this template to the next stage. Alrighty. So the next stage is going to be a PD, because so NC is using node connectivity to find out what else is going to change, and then PD is using the actual property of devices to determine what else is going to change. So that's a really important difference between those two. So B doesn't need to be highlighted anymore, so I'm going to cancel that. So now I look at the boldface. Now I know right away that the two components that I need to analyze because of this propagational delay time would be component X and component Y. So that is why the boldfacing is useful, because once you have a whole bunch of components, it becomes kind of difficult to find out, okay, which one just got one of the input pins changed. Then you have to compare between two snapshots, which is not going to be easy. But having these boldface here really helps, right? Because now I can tell right away that X has one of its input changed, Y also has one of its input changed. So now we have to basically try to figure out what would be the new output of these two components. It may not change, okay? Like in the case of X, it did not. Well, let's see. Both of them. I think I might have analyzed it incorrectly. I think I did. I think I wait. Let me think. Because it's a nord. Oh, never mind. Okay, I was okay. I was okay. All right, because X and Y are AND gates, right? So because X and Y are AND gates, so X dot out is continuing to be a 0. Okay, no change from before. So I'm making a note here because that means whatever connects to the output of X is also not going to change. Okay, in other words, the output of X is quote unquote a dead end when it comes to figuring out how the changes are being propagated, because it's not changed. On the other hand, when we look at Y now has both inputs being 1s, and since it's an AND gate, it is now changing its output to 1, and that means Y is now getting changed. So Y needs to be bold-faced, And I no longer need to boldface these two, so these two can now be unboldfaced like that. All right, and what else? Well, there's nothing else, right? Because I just tracked down all the things that were bold-faced before, and both components are now determined. So I'm gonna write down here, changed, and because both inputs are ones now. Okay. So I want to kind of leave myself a note of, okay, yeah, this thing just got changed. All right, so now we are going to copy and paste, and the next one is going to be NC again, node connectivity, and now we're just going to copy everything from PD from the beginning to the end. So if you want to use a table, that's probably going to work really well as well. Okay, and you can probably use some nice formatting like underline to kind of really distinguish, that this is node connectivity. So we can use underline here. They are just interleaved. NC and PD are interleaved because NC is looking at, like, in this case, an output that got changed, and then it's trying to figure out what is it connected to using the node, meaning this particular one, and by a node it connects to the first input into W. So that's why we have to alternate between PD and NCs, because NCs are really just looking at, okay, this thing here, where my mouse cursor is, just got changed. So what else is going to change because of that, right? So we look at the node and go like, oh, okay, we can see that the first input of W is also going to change, but that's the input of a particular device. So that's why. Okay, there we go. All right, so that's exactly what we are doing. Is we look at the connectivity from the output of Y to other components. In this case, it's not too bad. We're not looking at a fan out. Okay, now fan out means that one single thing connects to like a bunch of other things. So we don't really have a fan out in this case. It's really kind of one-to-one. So now we look at W in 0, and then we update it to a 1. Okay. So we say because y.out changed, and then we highlight W in 0 because now we basically note what is being changed, and this is now taken care of, so we can unbold it. All right, and that's it. Okay, because all we did was to track down what was bold-faced and then look at where they connect to. So we are now done with the NC phase. We are now moving on to the PD phase, or propagational delay phase. So propagational delay really is just looking at the nature of a device and ask a question of, okay, so if one of the inputs of this device is changed from blah blah to blah blah blah, how is the output going to be changed as a result? So there we go. All right. So now we know exactly which device we need to kind of try to refigure out the output. It would be W, right? So now we look at W, and I'm just looking at the, so we look at W, and we try to figure out W again, the output of W. So now we know one of the input changed from a 0 to a 1. Aha! Now because it is a NOR gate, so that means if at least one input is a 1, the output is going to be a 0. Okay, so now it is changed. So we're going to kind of put a boldface here, and then unboldface this one because that has been taken care of. Okay, we have utilized that change to compute the output of W.out. So it is now changed to a 0 because one input is a 1. And we are going to remove the rest of the explanation like that. Alright, so getting back to the text channel. I'm a little lost on what you copied paste when you move on to the next PD or NC. Can you explain that? Okay, so Chris is right. Okay, so let me just answer that one really quickly. So Chris is right, because when W.out is determined now, because it was a question mark before, changing it to a 0 means a change. So that means, now we can follow that particular node, and it goes all the way back to the first input of V. So that means we are not quite done with this stage yet. Okay, so we still have more things to track down. So getting back to Bilal's question, we are basically just alternating between NC, which has to do with how the wires are drawn, and PD, which has to do with the behavior of the individual devices. So once we are done with the PD, the next one is going to be an NC, because we are going to look at W dot out and find out, okay, what is going to change because W dot out just got changed. So we need to look at the node connectivity in that stage. So I hope that kind of explains it. Okay, so we have NC now, and oh, I meant to use uppercase. Oh, I think I just got caps locked. There we go. Okay, underline that, and and then every single time I copy and paste the entire thing, okay, as is, because that's the starting point. And then once I have everything copied and pasted, this is when I need to look back into the circuit and find out, okay, what connects to the output of W as a device. So I track down this node here. It connects to Q. So let's go ahead and highlight Q, because that's going to change because W dot out changed. It also connects to V dot in 0. So V dot in 0 is also going to get changed as a result. And those are the only two things, or those are the only two ports connected to the output of W. So once I have taken care of all of that, I unboldface W so that I don't confuse myself in the future and go like, okay, did I take care of that? Yes, okay, I took care of that already, and that's why it's not going to be boldface anymore. So I undo the boldface once I take care of something. All right, so what do we do now? Oh yes, okay. So now we have to find out, okay, what is the state of V dot in 0? Well, it's going to be the same as W dot out, and W dot out is 0. Okay, we say because W dot out is 0. And then we look at Q dot port, which is also going to be 0 because W dot out is a 0. All right. Are you guys still with me so far? I hope so. All right. So the next one is going to be PD, and I'm going to do an underline just so that it's easier to read. And guess what? We just copy and paste, right? Because now that we have figured out which device has one of its input ports changed, now we need to look at the device and say, after a certain propagational delay, are we going to change its output, or not, right? So now we need to take a look at that. Yeah, okay, that's good. Okay, it took me a few semesters to find out, this is the way to do it, right? Because in the past, I just look at the changes. So if I only track the changes, in order to find the current state of a certain pin, sometimes I have to scroll up, a few, a few pages or a few steps, and that's not easy, and it's easy to make a mistake. This way, it's harder. Okay, nothing is impossible. Okay. Nothing is impossible. It's just harder for me to make a mistake in this case. All right, so Q dot port being 0 is fine, because it doesn't really hook up to anything else, so we don't have to track that. Now V dot in being a 0, is a change from before. So now we have to look at the output of V and go like, okay, can we now determine the output of V? And the answer is yes, because now we can see both inputs of V are zeros. 0 or 0 is 0, and then you negate it, it becomes a 1. So V dot out, it becomes a 1 now. So we highlight it, and then de-highlight the other one, because now we have taken care of that specific boldface. So the reason why V dot in 0 was bold-faced is now taken care of. So now we have to change the explanation because, okay, so I'm gonna just kind of remove this portion, because both inputs, all inputs I should say, just in case it has more than 2, right? All input pins are zeros. So 0 or 0 is 0, and then not 0 is 1. Okay, so I'm just giving myself a brief explanation of why v dot out is now a 1. And some of you are looking at this picture and go like, oh no, we are not done yet, because now v dot out also connects to some things, so we need at least another NC stage and potentially another PD stage and so on. And you would be correct about that, because we have just used the nature or the device itself, in this case a NOR gate, to determine its output. So now we need to go back to NC and ask the question of, now that we know the output of this device has changed, how is that going to affect the ports of potentially other devices, because sometimes it can also feed back to itself, but in this particular circuit it does not. All right, so now we look at this NC, due to node connectivity, and we're looking at v dot out. So v dot out is connecting to two things. P is 1, so we highlight P just so that we remember that we have to kind of look at P and go like, okay, what is the output of P? What is the value of P right now? And it also connects to W. Let me track it again, because sometimes it's hard for me to see it. There we go. It connects to the second input of W. So now W in 1 also is going to be bold-faced. So that took care of the node connected to v dot out. So now I unbold-face v dot out, because otherwise I'll go back to analyze the same node again, and that would not be very productive. All right, so now we look at W dot in 1, and that's really just okay, so that's just a v dot out, and v dot out is a 1. Okay, so we say because v dot out equals to 1, and then p dot port is a 1 because v dot out is a 1. So I've just explained why W in 1 is now a 1, which is a change. All right, so let me get back to the text channel. All right, so FYI, it's Windows key plus Shift plus S to take a small screenshot snip tool. Oh, okay, all right. Well, since I don't use Windows, that's a useful tip for people who use Windows, which is probably like 95% of the class, but I don't, so I have a different tool to do that. And then Bernard said, I'm assuming that you can create some consistently flickering circuit like this. Not this one. Okay, so what Bernard is talking about is what we call an oscillator. Okay, and this type of circuit is not an oscillating circuit, so it doesn't do the flickering like that. Now, funny thing is, an SR latch can be a flickering device, but it will take both inputs to change from 0 0 to 1 1 in order to trigger it into that flickering mode. So when we have time, we can go ahead and analyze that, but right now we are going to be focusing on just this question. Yep, so it's kind of like an infinite loop, because the change is quote unquote self-propagating, so to speak. All right, so now we know W.in is changed. P is not too much of an issue, so we're just going to de-highlight a P dot port, because it's not a device, so it's not going to change anything else. But W potentially is a problem, so now we have to go to another PD cycle, and in this PD cycle we are going to look at the devices where the input has changed. So we copy and paste, and good thing I highlighted which one just got changed, because you can see there's a bunch of inputs, because there are 4 devices, each one has 2 inputs, so there are 8 input pins. I only need to care about 1 because that one just got changed. So because that one got changed, I need to look at the output of that specific device. So when we look at W, which is a NOR gate, now both of its inputs are 1s. So its output is continuing to be a 0. So so we will say continues. So this is no change, because it now has all inputs are 1s. There we go. So I do have to change the explanation a little bit, and it is important to note the node change here. Okay, so let me unboldface w in 1 first, and then I need to explain why it is important to note there's no change. Because if w.out has no change, that means we are done, okay? Because nothing else is now changed. So that means, everything is now, everything that can be determined are determined at this point, given the inputs are 0, 1, and 1. All right, so we are now ready for the next one. All right. Okay, so assuming we are ready for the next one, I'm just gonna copy and paste. If you guys have any questions, just put it into the text channel. All right, so the next one is turning C from a 1 back to a 0. So after I paste, I'm going to make that change here. So there we go. So that's going to be a 0, and this is going to be a node connectivity thing because this just got changed. C is changed. So now I have to track down the node connectivity from C to all the other components, and good thing it's only connected to one other thing, which is y dot in 2. So y dot in 2, y dot in 1, because we count from 0, is now changed. So we highlight this guy, and this is becoming a 0 because C just changed to 0. Okay, so I'm just putting a note here so that I remember, and this doesn't need to be highlighted anymore because the change has now been accounted for. But this one needs to be this needs to be bold-faced because I need to remind myself in the PD cycle next, Y is a device that potentially can have its output changed. So there we go. So we just copy the entire thing, and I have to remember to change the NC to PD because now we are in a propagational delay analysis. But I don't have to remind myself which device output I need to look at because Y is highlighted. So now I look at y.out, and we can now say, since Y is an AND gate and one of its input is a 0, so the output has to be a 0. So this is now changed because one of its input becomes a 0. So I'm going to name that one specifically. So we'll say because y dot in 1 becomes a 0. So this way I have it explained. So that's useful. And since y.out was changed, I'm going to highlight it, okay? Because the next stage is going to be a NC stage because I need to look at the output of Y and find out what connects to it using a node. So now we are ready to move on. Oh wait, I have to unboldface this one because otherwise I will confuse myself. So I have to unboldface it. And I have no idea why it now determines that I have a spelling problem and it never happened before. Alrighty. So we copy and paste and change the name of the stage from PD back to NC again. So now we look at y.out and find out what it connects to. It connects to only one thing, which is W in 0. So we look at W in 0, automatically highlight it because it is the one that is potentially changed. So it changed from a 1 to a 0. Okay. Changed because y.out becomes 0. And then remove the rest here. Alright, and now we can unboldface this one because it's taken care of. And then we are ready to move on to the next stage, which is a PD. Alright, so let's see. So you only keep the .out part bolded in your PD part. Correct. Okay, because in the PD part, you're basically potentially looking at an output pin being changed. Now, but you don't boldface unless the output is changed. So it can be changed from 0 to 1, 1 to 0, unknown to 1, unknown to 0. Those are all changes. So W dot so in this case, we have just used node connectivity to figure out that W has one of its input pin changed. So the next one is going to be a PD stage, and we need to look at the output of the W component. So we copy and paste, copy, and then paste. And now we look at W.out, and we ask the question of, okay, is that going to change? And the answer is it is not going to change because one of its input is still a 1. So it will still be a no change, but the explanation of the no change is no longer that. It is going to be because W in 1 remains a 1. So the output is going to continue to be a 0. So that means we are now hitting a dead end for this part of the question because there's no component has the output changed, and that's why the NC stage is not going to change any other input pins anymore, and as a result we are done with this part of the analysis. Alrighty, so now the next one is 110. Okay, so we are going to copy the entire thing. And I think this is a whole lot better compared to what I used to do, which is just noting the changes, and then I have to go back up and find out, okay, so what was the last time I changed something and what was the value at the time, and that turned out to be like really difficult to track. It's just it's just very tedious, and it's very error prone. Alright, so this is just changed because someone decided to change one of the someone just decided to change the state of an input pin. So now I have to look at where does it connect to, because this is still an NC or node connectivity stage. It connects to the first input of X, so X in 0 is now changed to a 1, and we say because A is changed to 1. But I also have to remember to highlight this one because it just got changed. Nothing else is changed, so we are okay, we are good with the NC now. And after the NC, we have a PD. So basically, you have to remember that you have to alternate between NC and PD. So now we have PD, and X is the component that I need to analyze because one of its input got changed. And because now X dot in, both input pins are 1s, so the output is now a 1, which is changed. Okay, so I'm going to put changed in parentheses here, and then I'll explain why it is now a 1. So because both inputs are 1s and X is an AND gate. Okay, so now I highlight the output pin and unhighlight the input pin because the next stage is going to be a NC stage. Okay, because now we need to look at what X.out is connected to and then find out how that is going to affect the input pins potentially of other components. So you look at the output of X and it goes into the second input of V. So now we oh wait, I forgot to do one thing, didn't I? Yep, because I forgot to change the PD to an NC because we just changed an output pin. So this is an NC node connectivity stage. Alright, so based on the connectivity in the diagram, X connects to V in 1. So V in 1 is the one that is now changed to 1. And then we highlight V here because that means in the next PD, V is the component that we need to analyze. X is no longer of interest to us. There we go. So now we can move on from NC back to PD. And remember, the first thing to do is to change the header to PD. And now we look at the one that's the one or ones that are bold-faced, and only V is bold-faced in this case. So now we have to ask the question: is the output of V going to change? And the answer is yes. It's going to change to 0. This is changed. And the reason is because at least one input is now a 1. So we'll just explain because V in 1 is 1, and this is a NOR gate. So with a NOR gate, if at least one input is a 1, the output is going to be a 0. So we have to highlight V.out so that I can remind myself in the next NC stage, which pin, the connectivity of which pin do I need to analyze. As you can see, at this point, this is just kind of chore. So now we get back to NC, and we look at V.out. So V.out is one of the more troublesome one because it goes to two places. The first one is not too bad, because it's just going to P, and I'm gonna highlight it, because just in case I forget. And then the second one goes to W in 1. So W in 1 is the other one. So I'm gonna highlight it. So you can see that I don't change the input pins, because an output is changed until I have highlighted every single one. Because this way I'm not gonna forget. As I change something, I forget. Oh, but of all the nodes of all the pins connected to this node, which one did I highlight? So I highlight them all first, and then I go to every single one and then change the state of that input pin. Alright, so now we can say, okay, so all of these are connected to V.out, and V.out is now a 0. So V.in 1 is just changed to a 0, and then P.port is now also changed to a 0, and the reason is the same thing. Alright, so now I can unboldface this one, and then move on to the next stage, which is a PD. It just takes a long time to explain things when I'm also typing. All right. Okay, so we are moving on. So P is not too big of a deal. There's no propagational delay with an output pin, so we can just kind of not de-highlight it. And W is not. Okay, W is a gate, so the output can potentially change because of the change of inputs. So now we look at the W.out. It is continuing to be a 0 because it's a NOR gate. So if at least, oh wait, okay, I just contradicted myself. Both inputs of W are zeros now. So 0 or 0 is 0, but since it's a NOR gate, it is negating that 0 to become a 1. And the explanation, so it is changed. Okay, so we're gonna have to change that. It is changed because, changed. And we're gonna explain that because both inputs are zeros. There we go. And because it is changed, we highlight it. And you guys will go like, oh no, that means we have to go to another NC stage. Yes, we have to go to another NC stage. There we go. And paste, and here's the NC stage. Alright, so in this particular NC stage, we have to look at the connectivity of W.out, and you guys are going like, no, it changes a few things, not just one. And you would be correct. W.out connects to Q, so Q is going to be highlighted, and this one is going to be the easy one to deal with. So, and then the other one is W.out connects to V in 0. So we have to highlight V in 0. Okay, so now that everything connected to the same node are highlighted, then I go in and actually make the changes. So W.out is a 1, and that's why V in 0 is now a 1. Make sure I change the comments to be consistent. And then the other one is going to be the same, which is Q here. So Q.port is now a 1 because W.out is a 1. Q is not an actual device, so there's no propagational delay to analyze with that one. W.out is now, all the connectivity of W.out is now, taken care of. So I'm going to unboldface this. So now we have V.in being changed from a 0 into a 1, and now I have to go back in and figure out what to do next. Now I'm gonna give you guys a tip here. Okay, if at this stage here I forgot, oh, what just got changed? Okay, if I forget that, there's a tool within a Google document that can really help. Because it track all of your changes. So if you type Control Shift Alt H, yes, all three of those keys, it will get into a history mode, and once you're in the history mode, you can actually go to a particular time frame and find out what you changed at that time frame. So if you go to one specific time frame, there are 4 edits, and you can just kind of scroll through the 4 edits. So now I can see, oh, okay, so Q.port is changed from a 0 to a 1, and so on. So this is a useful tool, if you ever lost track of, okay, but I cannot remember which one got changed. This is a really useful tool, so you can actually find out, how you have edited, parts of your document. All right. So now we have to move on, to PD, because one component has at least one of its components changed, or one of its input changed. So now we have to look at the same component and ask whether the output of that component is going to change or not. Alrighty. So now we have to look at v.out. V is a NOR gate. And both inputs are 1s, so 1 or 1 is a 1, but since we have to negate it, it is an output, so it is now unchanged, okay, because both inputs are 1s. There we go. And then we unboldface this input pin because we have taken care of the device that needs to be analyzed because of that, and we can see that there's no other boldface anymore, so that means we are done with this entire stage. Alrighty, so I'm just looking at the time. This is taking up too much time, but we are done. We are done with question number 1. Now we move on to question number 2. Alright, so I think we got enough time. We still have 20 minutes. So question number 2 is about the processor architecture, and I really hope that most of you have time to kind of look into it the way I suggested. So I'm going to look into the processor right now, and this is no longer needed. I don't need this circuit here anymore, so we can take that out. And okay, so I just need to bring up the processor. So that's under Documents, CISP310, River Spider Processor. Okay, there we go. Alright, so now we're going to take a look at question number 2. Alright, so question number 2 gives you the values of the tunnels in base 10, and it's asking you, first identify the components that is going to be updated or changed on the next rising edge of the clock. Okay, so now you have to think about, what is this asking about? What components can possibly change or update on a rising edge of a clock? Well, that would be basically all the registers except for the microcode pointer, but a register needs to be enabled first, right? So you have to look at things that are enabled. But then you think, because you can use Logisim if you want to, during the test, but it's not going to be super duper helpful. It is helpful, okay, but it's not going to give you the answer because you don't know which one is a 1, because you have to go back to here to find out how these names of the tunnel correspond to what is enabled, right? So that's why going through the exercise that I did in class a few times would definitely help, because that will help you associate tunnel names to specific registers or potentially registers that will be enabled. So right now I can see PCEN is a 1, so that means the program counter is going to be updated. So I'm going to identify that as the program counter. But we'll see what else is going to be updated here. Okay. We can see RIEN is a 1. So if you look into the circuitry here, RIEN is this one here. So it would seem like it's not going into any specific register, but you don't know because it goes into a component that is quote unquote a macro. So you really have to kind of look into the register bank and find out where uh, input enable is connected to. So it connects to here. So you look at this and go like, it doesn't hook up to any registers, so I think I'm safe. No, you're not. Okay, because it does go into a decoder, and a decoder is like a demultiplexer, except the input is a constant of 1. So now the question is, which register am I selecting from register input select? And that you have to look at the question, right? So RI cell is 0, so that means register A is the one being selected, because that 0 translates to a bit pattern of 0 0, which then goes into the decoder. And a decoder is like a demultiplexer, except the input is constantly a 1. So now that it is enabled, and we have 0 0 as the selector, so that means this wire or this node is going to be a 1. So that means register A is enabled and is ready to be updated. So that's why in the answer we also have to write down to register A. Let's see, there's one more thing, okay, because this one is kind of misleading, because it doesn't seem to be enabling anything. This is the representation of bit 0 of the D port of ROM. Okay, so now you have to look into the circuit and find out where that thing connects to. So let me go back to the main circuit, go to the ROM component, track down bit 0 of the D port. So you just click on this wire and it connects to the enable of the instruction register. So the instruction register is also going to be updated at this, in this particular question. So I'm going to have to write down instruction register, like that. Alright, so let's see what else may be updated, because RAM is also sensitive to a rising edge, if it is in the right mode. So we want to look into RAM, and even though RAM is selected, LD is a 1, which means it is not in a write mode and it's in the read mode, and you cannot update RAM when it's in the read mode. So RAM is not one of the components that we should list here because it's not getting updated. Alright, next, identify how these components are updated. So we know PC is going to be updated, we know register A is updated, we know in the instruction register is going to be updated. So we want to find out, how those things are going to be updated. So now we have to look at the connectivity between the components. Okay, so we need to focus now on the multiplexers and the demultiplexers and find out, how they are establishing pathways between the components. Alright, so one thing at a time. Okay, so one thing at a time. We look at PC first, and we look at PC, and it's updated by this multiplexer, and this multiplexer is controlled by PC mux. So now we have to figure out, okay, so what is going to be PC mux? Because okay, so that was explained earlier. Because there's a decoder here, and this decoder connects to this selector. This particular select is 0 0 at the time, which means output 0 of the decoder connects to quote unquote the input. But remember what I said, a decoder is like a demultiplexer. The input is always going to be a 1. Yeah, so that. Right, so now I have to, oh yes, I remember now. We have to find out what is PC mux. So PC mux is not a tunnel coming out of the ROM. So PC mux, as we explained it the other day, is actually here. So now we need to look at PC mux, and in the question, PC mux is a 5. Okay, so we have to look at input 5 of that multiplexer and find out what it is. So you can see this is input 5 right here. Okay, and it's connected to a constant of 0. So we know now that PC mux is going to be a 0, and that means it's just going to increment. So PC, the program counter, is just going to increment. So I'm just going to say PC. Alright, so right here we say PC increments because PC mux is 0, and that's because PC mux is 5. So that's acceptable as an explanation. And now we need to look into register A. All right, so register A, okay, so you want to look into the register bank. Now, ideally speaking, you don't want to do it during the exam, okay? But to answer the question, you have to go into the register bank and find out that register A's D port connects to register in, which in the main circuit is this in wire over here. Okay, so it is coming out of a multiplexer. So now your job is to figure out, okay, so which input of this multiplexer connects to the output of this multiplexer. Now we know this multiplexer is going to be enabled because RIEN is a 1 already. That one that we have already established in an earlier step. So the question is, what is RI mux? Okay, because if RI mux is a 0, that means we need to look at this wire. If RI mux is a 1, then we need to look into this wire. So we go back to the question and look up what is RI mux. RI mux is a 0. Okay, so if that is a 0, okay, got to the wrong screen. So if RI mux is a 0, that means we are looking at this input here, and that one connects all the way to the data port of RAM. All right, so let's see how we should document it, right? All right, so now we say reg A is connected to ram.d. So now we have, so every time you have anything to do with RAM, the next question is, but which location? Because we just know that the content of some location in RAM is going to be used to update register A, but what is determining that location? So in other words, what goes into the bracket here, because it's an array. Okay, we need to know how the address port is connected. So now we go back to the circuitry here and go like, okay, now we have to figure out where A is connected to. It comes from the multiplexer. Some of you may recognize this type of analysis already. It's just we were doing it in a slightly different way before, but it's kind of the same thing. And I'm not going to take row today, so if anyone is concerned about taking row, I'm not going to take row today. So we have to look into address mux because that's the selector of this multiplexer, and that's in the question, right? So the question has ADDR mux being, all right, so where is it? ADDR mux is here. It is a 1. All right, so if ADDR mux is a 1, that means we are looking at this wire here. So we now know that the PC, the program counter, connects to the address port. All right, so if I go back to my answer here, I can now either put something like this, or alternatively, we can say register A gets whatever program counter is pointing to. And the program counter is also incrementing, okay? So that is true. Okay, so next question is, what about the instruction register? The instruction register is easier to analyze because it only connects to one thing. There's no multiplexer to switch the input into the instruction register. So the instruction register is here, and if you click on the input of the instruction register, you can see it's coming from the data port of RAM again, and we already know how that one is outputting. So that would be easy one to kind of answer. So we can say instruction register is also going to get whatever the program counter is pointing to. So that answers this particular part. And now it asks, does this microcode slice remind you of an existing instruction? Well, what do you think? I believe this is actually one of the first instructions that we have analyzed once we started to talk about the processor. So which instruction has this type of thing happening? The program counter is auto incrementing, and then one of the 4 registers is getting the content of a particular location that the program counter is pointing to, and then so which one comes the closest to this? Yep, you guys are correct. Good job. Okay, I need to use this thing once in a while. Okay, Yeah. Good job. Good job. It is indeed LDI. So it would be LDIA of something. That's something you don't know because I did not tell you about the content of RAM, so therefore the question mark you can't really answer what that question mark is. However, you can answer what the opcode is. So let me go back to the opcode table. We now know this is LDI, and we know the register that is going to be initialized is register A. So once we get here, we just search for um, control F is for finding, and then we just look up LDI, and the pattern is 0110, which is a 6, and then a 11, and then X in this case is 00, so that means 1100 is going to be a C, so 6C is going to be the opcode. So now we can go back to the question, which I cannot remember which tab is anymore. Nope, that's the wrong class. Oh, okay, so which one is it? Good thing I have this little tool here. Okay, it's really handy if I need to find something. There we go. So the opcode is, it needs to be in hexadecimal, so we need to make sure that this is in hexadecimal. 6C, there we go. Oh, 6C, there. Alrighty. Douglas knows that exam. Alrighty. So that answers question number 2, and now we move on to question number 3. All right, so question number 3 is it's interesting from the perspective of what I can do or what I have to do, because there are tools on the internet that can help you determine all the bit patterns once you know what value you want to represent and which IEEE floating point format do you want to use, and it just kind of goes through the whole thing automatically. You say, okay, I want to represent, let's say, 1.25, and then that tool will give you the actual bit pattern of 1.25. So it makes no sense for me to ask a question like that. Okay, this is the value that I want to represent. Show me, what bit pattern is going to represent that value. The other way around is the same thing. Okay, there are also tools online where it will say you just give it the bit pattern, like all 64 bits, and it will tell you what value it is representing. So once again, it doesn't make any sense for me to ask that kind of question. So it takes a little bit of thinking to think of what kind of question I can ask in order for the question itself to be meaningful, because I don't want to know whether you know where to find a tool to help you find the solution. I want to know whether you understand the material so that you know how to find the solution. So that's the challenge. That's my job, right? It's part of my job. So this is a question to kind of address that. A 64-bit pattern presents a value v1 of 1 times this number times 2 to the power of 10 using the correct IEEE double precision floating point number interpretation. First, figure out the binary pattern of the IEEE double precision floating point number representation of the value v1 as a 64-bit pattern represented in 16 hexadecimal digits. Show all steps. Okay, so this is why it is super duper important to show your steps, because if people don't show their steps, I'm just going to make the assumption that it was coming out of a tool and it is not going to have any point values associated with it, with that answer. So you guys will have to show me all the steps. All right, so now how do we figure out the bit pattern? Finding the tool is understanding. Well, it is the understanding of finding the tool, knowing how to find the tool. That's what you're understanding. That's what you are demonstrating that you have understood, is how to find the tool, not how the tool works. So I would accept Chris's argument that it does show some kind of understanding, except it's not the kind of understanding that I'm looking for. All right, so you look at this number and go like, oh man, this is going to be tough. Well, it's not going to be that tough, okay? Because what you can do is to say, okay, I already know it's raised times 2 to the power of 10. So you can just say, okay, let's find out what value we are actually dealing with. So you can just say 1.109375 times 2 to the power of 10 is, and I personally would just kind of use a spreadsheet to do it, right? Spreadsheet is basically a very fancy kind of a calculator. So we'll go ahead and use a new spreadsheet. All right, so we'll go ahead and type in this entire thing. So just kind of copy and then paste it into a cell. So put the equal sign first, paste the rest, and it's 11.36. No, it cannot be that easy. That doesn't sound right. I think I need to change the accuracy because that doesn't look right to me. All right, so we need to change number format. Okay, so we need to change it so that it represents all the digits. So it's going to be a number scientific. Nope. All right, so let me crank up the magnification because I can't see where there's a comma. It is a comma. Okay, that's better. Okay, so that turns out to be 1,136. There we go. Okay, there's some traffic going on. Let me take a look. Um, it is acceptable because the copy and paste is not from the other thing back here. I manually typed 1136. So it's perfectly okay because it's copying in the other direction. You can always copy stuff from your document into something else, and I just hand copied the value of 1136 back into the document itself. So that is definitely permissible. All right, so now I need to convert 1136 into a binary number. So if I see something like a bunch of zeros and ones right away, that also will have points deducted because that person is not showing me that that person knows how to do base conversion. So I'm going to do it by hand, right? So there's a 1024 in it. And after the 1024, we have how much left? So let's see, we have 112 left. So that's going to be 1024, and then I look at 112 and find out what is the largest power of 2 in there. That's a 64. And once we take care of the 64, there is a 48, I think. So 48 is a 32 plus a 16. There we go. All right, so I'm going to copy in the opposite direction again just to verify that my mental math is correct. So just kind of, okay, let me show you how I did that, how I'm doing that. So put an equal sign first and then the summation. Yep, I got it. All right, so after using my mental math to come up with a sum of powers of 2 to come up with the same value, now I can say this is 2. And if you want to use caret to represent to the power of, that's fine. So this is 2 to the power of 10, which is the 1024, plus 2 to the power of 6, and that's the 64, plus 2 to the power of 5, and that's our 32, plus 2 to the power of 4, and that's our 16. So once you get to this point, you have demonstrated enough about how to do base conversion yourself. So now we can just go ahead and write the binary number. So the binary number is going to start with 2 to the power of 4, which is 1 followed by the 4 zeros. And then we have 1 times 5, 1 times 2 to the power of 5, 1 times 2 to the power of 6, none of the 7, none of the 8, none of the 9, and 1 of the 10. So that's how I come up with the bit pattern, like that. There we go. All right, so any questions about that? Now, you can use a calculator. It's just that after you use a calculator, you still have to explain to me what it means. Oh, okay, yeah, okay. Yeah, I usually get that, like, oh, okay, now that you explain it, it doesn't look too ugly anymore. And then it's when it's time for people to actually do it in class, they go like, oh no, this is actually really ugly again. Okay, but I'm not done yet, okay, because this is just the number in base 2, right? So I have other things that I need to do. So this is not in a double representation. This is just a binary number, and you can also kind of emphasize that there's an implicit decimal point or binary point right here. So the first thing I need to do is to turn it into 1 point blah 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 blah. Okay, so that means I'm gonna have to say, all right. So let me just change the format a little bit here. This is the nice thing of using an editor to do everything, because you can easily use copy and paste, and then change the format and stuff like this, right? So now I can say, okay, this is the same as 1.000111, and the rest of the zeros I don't really need to represent. And now I need to say, okay, times 2 to the power of what? Okay, because that is the whole idea of a floating point number. You have a mantissa, and then you have a power of 2, because we are dealing with a base 2 scientific notation essentially. So now the question is, what should I raise 2 to a power of? How many times did I move the decimal point? Nope, it's not 6 times. It is not 6 times. Is it 10 times? I cannot remember. Let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sure enough, it's 10. Very good. Now, it kind of makes sense, right? Because, 2 to the power of 10 itself is 1024, and we can see the value being represented is 1100 something. So it is just a little bit more than 1024. So having 1 point blah 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 times 2 to the power of 10, which is 1024, makes sense. Okay, so this is the kind of quick mental math that you can do to have a sanity check of whether your answer makes sense or not. All right, so very good. So now we have all the components, right? So we have all the components. We are going to specify the exponent, the exponent component is going to be biased, right? So the biased amount is 1023. So we say is 10, which is the intended power of 2, plus the bias amount, and that turns out to be 1000 and what? 33? Yep, there we go. And that turns out to be 1024 plus 11, and 11, no, hold on, not 11, 9. 9 is even easier, because 9 is just 8 plus 1, and that is now, there's a 1 1, no 2, no 4, 1 8, no 16, no 32, no 64, no 128, no 256, no 512, 1024. So that's because it's called a bias. Okay, this is the bias, and to understand this part, you kind of have to go back and read the floating point number representation module, or rewatch the video. Okay, because the bias is just a constant that we have to add in order to figure out what bit pattern is going to be the exponent. Yeah, so that is the exponent, and there should be 11 digits to it. Okay, so let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so there are in fact 11 digits, and so we're good. Okay, so I'm just counting the number of digits. And if someone is going to ask me, but how do you know there are supposed to be 11 digits? I'm just going to say that. Yep, that's why it's important to get my webcam on, because that's my answer. It's like that. That means it is in the module, and people are supposed to read that module or watch the video of that discussion. That's basically what it means. All right, so there is that, and we need to figure out the sign bit. So the amount that I specify here is not negative, so that means the sign bit is going to be a 0. And what we call the mantissa is really just a fraction of the mantissa. So fraction of mantissa is the rest of the bits, not counting the 1 point. It's just really the rest of it. So it's going to be this part. Okay, so I just copy and paste it here. Except, it's going to have a bunch of zeros after that. Okay, because how many digits do we have in the fraction of the mantissa in the double precision floating point number? And you guys are going like, how can we possibly remember something like that? Oh, okay, Mark is too quick. Mark is too quick because I was just about to explain, based on what you are seeing here, we already know what is that number because 1 bit is being used for the sign, 11 bits are being used for the exponent of 2. So how much is left out of 64 bits? 64 minus 1 minus 11 is 52. So there are 52 digits here. So you just have to fill in enough zeros to make it 52 digits. All right. So that means, as a in binary representation, okay, not as a in binary representation. So we have basically a 0, which is our sign, followed by the exponent, which is this bunch of zeros and ones. Right, there we go. And just paste it here. And then the rest are the mantissas, or the fraction of the mantissa. So I have to be super careful because it is not the mantissa itself, it's just the fractional part of the mantissa. So now we have the binary representation. Same kind of answer as what I have already explained earlier. That's basically the format. That's how double precision floating point numbers are. That's what the standard specifies. Okay, so you're gonna have to go back to that module and read that part. I know how much people may not like that kind of an answer, but I think it's important that you guys know where to find the answer and not to rely on me to tell you what the answer is. So I'm going to tell you how to find the answer. I'll give you the pointer, not the value. So you will have to do the dereferencing yourselves. How about that? Using a programming concept to explain concepts in a programming class. And yet it is not recursive. That was an article that explains how the meaning of LOL has changed over time. But that's definitely a digression from what we are dealing with here. I think we got enough digression for a while. Alright, so I break it up into chunks of 4 because one hexadecimal digit is representing 4 bits. And this part you can use a lookup table. Just use a lookup table. This is a 4, this is a 0, this is a 9, this is a 1, this is a C, and the rest are zeros. So how many zeros do I need? Well, the question is how many hexadecimal digits do I need to make up 64 bits, right? One hexadecimal digit corresponds to 4 bits. So how many hexadecimal digits do I need to make up 64 bits? The answer is 64 divided by 4, which is 16. I got 5 already, so I just need to pad it with 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Done. All right. So there is that part of the answer. Okay, so this is the answer of the first part. So the second part is the part that is going to require some of your brain juice. Because next it is discovered that the binary bit pattern in the previous step was erroneously created from the original value of V using the incorrect assumption that there are 9 bits for the biased exponent. other than just the bit width of the bias component part, the positioning and meaning of the bits are correct. So that means we're still using the sign bit as the most significant bit, followed immediately by the 9-bit now, which is erroneous, for the exponent of 2, and then followed by the fractional bits of the mantissa. So the ordering is still the same. It's just that I make one mistake of using 9 bits instead of 11 bits for the 2's exponent of 2, and at the same time, instead of using a bias of 1023, excuse me, I'm using a bias of 63 instead. Based on this information, devise the original value V that was supposed to be represented. Again, you'll show all steps. All right, so let me reread this question because I have to find out, Okay, so now based on the incorrect assumption, I'm going to have to come up with another bit pattern here and then reinterpret that pattern using the correct double precision floating point number and find out what value was actually represented. So that is going to be the fun part, okay? Because, well, for the most part, it's not really that much different compared to this process. So I can actually copy and paste a portion of it. Not all of it, but at least, up to this point here. All right, so does everybody understand what the question is asking? Okay, let me highlight what is changed here. So what is changed here is the erroneous assumption changes the bias from 1023 to 63. So that means we end up with 73. Yep, 73 here, and then we have to re-express this as a binary number, but using 9 bits. So that would be 64 plus 9, which is 64 plus 8 plus 1. And that would be 1 followed by 6 zeros. That's the 64. 1, 2, 3, 4, 5, 6. And then this is a 1 for the 1. And then this is a 1 for the 8. Okay. And let me double check. So we are using, let me double check here, 9 bits. That doesn't look like 9 bits to me. I'm using a 63 as the bias. Okay, so if the question says I'm using 60 for 9 bits for the bias, I'm gonna have to pad it to 9 bits. Yeah, the bias amount is supposed to be 255, but since the question said, oh, right, okay, fine. I did not read my own questions carefully. Duh. Okay. All right, that's supposed to be 255. You guys are correct. So it's 265, and just have to change this one to 256. And it used to be a 64, so 64 would become a 0. 128 is also a 0. 256 is a 1. So let me just count. There should be 9 bits here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's correct. All right. Sign bit is still a 0. So now the mantissa is still the same. The fractional part of the mantissa has not changed. So when you concatenate all the zeros and ones, then we end up with a 0 for the sign. We end up with this particular bit pattern for the exponent. And then we end up with the rest, which is this portion for the mantissa. All right, so I'm going to comment here and say this is the erroneous way to represent the original value of V. All right, so now we want to look at this bit pattern and say, so if we look at this bit pattern using the correct double precision floating point number representation, what would that value be? Now, you guys remember earlier that I said, yeah, there are tools that can do it, right? So, but since the question said, answer here, show all steps, and it does not mean to show all the steps of how you found that tool and what you entered into that tool and how you copied the answer from that tool into the question here. Show all steps means you are showing all the steps to do the actual computation and explain what those steps are. So because I know some people are very good at arguing, myself included, so I can actually twist my own words to say, but you said just show all steps, and I showed how I took screenshots of how I found the tool, how I entered the value into the tool, and how I copied the tool into here. I have shown all the steps. Why am I not getting the points? So I just answered my own question. I'm a very bad student. I can be a very bad student. Extremely bad. All right. Yes. I was expecting LOL in the text channel, but I guess you guys are too tired to actually type anything here. All right, fine. I'm going to do this. Uh-oh. Am I out of battery? Okay, that's good. There we go. Alright, so now we look at this and we basically break it up again. Okay, so we copy and paste it, and then we say, okay, interpret the bit pattern the right way. So this involves me to look at this bit pattern and basically break it up again, but this time I'm breaking it up using the correct format for double precision floating point numbers. So this is still the sign, and then we have 11 bits for the exponent of 2. So there'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. Oh, I think that's still correct or not. Now those are 10 bits only, so that's 11 bits right there. All right, so now we have to recombine all of these things. So the sign bit is still a 0. That's an easy one because nothing changes the sign bit. So the exponent bit pattern is 1 followed by 4 zeros and then 1 0 0 1 0 0. That is 1024 plus a 32 plus a 4, and that turns out to be, come on, mental math, 56 plus 4, 60, so 1060. And that means the actual power of 2 is 1060 minus 1023 because that's the correct bias for the IEEE double precision floating point number. And that turns out to be 57, I think. No, it cannot be 57. It's 37. There we go. So this is 37. And then the actual mantissa is going to be 1 point and then followed by this particular bit pattern here. So, I mean, obviously, there's no need to copy that many zeros because, the last significant digit that is a non-zero is this one here. So that is in base 2. So that means the actual value is, okay, so this one is, basically 1, and let's see, we got a 7, 1 plus, 7 divided by what? That's a 2. This is a 2, 4, 6, 8. That's a 16. So it's the 7/16. Okay. So the actual value is 1 plus 7 divided by 16, and then the whole thing times 2 to the power of 37. So this would be acceptable as an answer. In other words, you can give me just the expression and not actually fully resolving it. But at this point, fully resolving it is not going to be too much trouble because I can now go back to my trusted spreadsheet and just specify what I specified over there. 1 plus 7 divided by 16 times 2 to the power of 37. And that turns out to be Just need to have enough digits. So that turns out to be the correct answer. Um, but leaving it like this is already sufficient, because the very last step is just punching in the the actual expression into a calculator. So that's not too significant. All right. All right, so we got the whole test. The first part took a long time, just because it's a very tedious process. Any questions? Yeah, so the first part, I'm going to modify it so it won't have as many stages. So it won't take up all the time just by just doing the first question. Because if you okay, this is the other thing that's nice about Google Document, is it documents the time as well. When did I do what? So you would find that question number one took a long time, just because it is tedious. So by reducing the number of stages, for question number one, there will be enough time for the other two. Now, once again, I cannot guarantee the format of your questions. So, but I can only guarantee that I'll be testing you on how you propagate changes through a circuit, and you can almost guarantee, you can almost count on not being the same circuit here, right? I mean, it's so. So that's going to be one kind of question, is to test whether you understand how to propagate changes through a circuit. And also depending on the input pins, do you know how to update the states of the circuit after that? So if somebody is to ask me, but I can do all of this using Logisim, well, the question is, can you? Yes, it will be April 7th. So the question is, can we do all of this using Logisim? I'm going to say you can use Logisim to verify your final answer for each stage, but Logisim cannot give you the part of the answer that's going to count for points. And that's the reason. The reason why is because Logisim always gives you values for everything, right? So when you look at any particular stage, Logisim will, it cannot give you the intermediate analysis between the settled states, of corresponding to certain types of input pins. So that's why Logisim is helpful if you want to only confirm the very last one for each state. Okay, so for every time we change the input pins, this is the one part where Logisim can help you confirm, but it won't give you all of this stuff here that derived the final actual states of everything at the end of each part of the question. So before anyone said is trying to say, okay, I'll just use Logisim to answer this question, the answer is it can help, but it's not going to be able to give you the actual answer. So for question number two, we don't need to show the actual process of getting to the updated components, just simply which ones are updating and how they connect. Yes, so for the second question, okay, let me scroll down to the second question first. Keep going, keep going. You can kind of imagine how long it took me to grade this before I came up with this type of representation, because I need to go back and forth, back and forth. I actually need to draw circuits out to kind of cross out the values and then update the values and then cross out the values, to and then give partial credit to people who actually got some of it right and some of it wrong. So that took a long time. All right, so getting back to question number two. So question number two, the first part is really just asking which components are getting updated. Let me see here. Trace your reasoning to the bits from the data port of ROM. You may refer to these using the names. So you can, so to answer my own question, okay, to get all the credit, we have to say PC because PCEN is a 1. Register A. Now this one is harder because it actually takes several tunnels to determine this. So we have to say because RIEN is a 1, and then RI cell is a 0. So because of both of those reasons, register A is part of this answer. The next one is just that rom.d bracket 0 is a 1, and that's it. And then for the second part, um, identify how these components are updated. For each component that is going to be updated, identify how it is going to be updated. Column C of the opcode table is a good example of what this part should look like. So, so you can see how reg A is getting asterisk of PC. That's one thing that we have seen in column C of the opcode table. Let's see, and explain why you think this is how it is going to be updated. So you have to look at the multiplexers, and possibly other components that are configured by various bits coming out of the ROM. I'm gonna change the question so that that part is not in the question. So this way, you can kind of make it a little bit shorter and just kind of look at it like this. And then the third part is, does this microcode slice remind you of an existing instruction? Find the instruction that overlaps the most with the given microcode slice of this question and determine the exact and specific mnemonic of the instruction. So I gave you an example here. Use the following area to answer this part of the question. So this part is okay. And it even explains how you use a question mark as a placeholder for the part of the mnemonic that cannot be determined. So in this case, the actual value of the immediate operand cannot be determined. So that's why it has a question mark here. And then the last part is, what is the hexadecimal opcode corresponding to this mnemonic? Use the following area to answer this question. So just giving me the hexadecimal digits should be sufficient. There we go. All right, so we have the whole thing covered, and hopefully, question number 3 does have a part where you have to read the question carefully and find out what it's really asking. So in the actual exam, and you're not quite sure what the question is asking, you can go ahead and ask me for clarification. Okay, so Chris is asking, how do we know it is LDI? And that you have to go back to the opcode table and find out, given that we can determine that this is what is happening when the instruction executes, then you have to go to the opcode table and find out which instruction resembles what we saw earlier the most. And in this case, it turns out to be the LDI instruction. So that's how we figure out that specific answer. Yep, all right, you're welcome. Alrighty, so anything else? I mean, you guys all have access to this document now, so you can refer to it, from time to time. One thing I want to not so much warn people, but to point out is, don't over prepare assuming your question is going to be exactly like this. So you're just super duper practicing this process. That is not likely to be productive. What is likely to be productive is really to understand what exactly is the 64-bit double precision floating point number representation, what each part is representing. What technique do we use to figure out which part, and so on. So you want to break it down to to a fine component, or techniques that are just addressing just smaller points, like how do we convert to base 2? Okay, this is the conversion stuff. And how do we figure out the fractional part of the mantissa? Well, we first have to find the mantissa first, right? Then we can find the fractional part of the mantissa. To repeat some of the questions that you guys have asked earlier, is what is this 1023? Where is it coming from? Well, it's coming from the standard. Okay, the standard specifies we have to have 11. We have to use an 11-bit unsigned integer that is biased by 1023 to represent the actual power of 2. That's how we got the 1023. So. Alright, so let's see. Will you be providing questions like the previous exam in the questions text channel with answers? I'm not really sure what that is asking. Let me parse that question again. Will you be providing questions like the previous exam in the questions text channel with answers? Well, I just gave you one, right? I mean, this is your I mean, we spent today's entire class to give you the answer to the sample questions. Yeah, there's no lab today because I think some of you probably are getting a little tired just by watching this. Yep. And let's see. Oh, okay. For more study material. Hmm. Okay, let me click on the screenshot and find out what that is. Okay, so those are not exam questions. Those are just kind of random questions that I came up with. So one thing you can do, one thing you can do is to go back to the SR latch module, the memory device module, and just type in or enter one of the devices into Logisim, and then you basically give yourself questions kind of like the first one. So except in that case, you are using a circuitry that is actually in the module. So even though I told you that it's unlikely that you will see exactly the same circuitry in the module, unless you really already have a really super duper thorough understanding of the circuitry and you can do all the simulation of what is getting updated between the NC and the PD, time slices, that's just as good as an exercise. Okay, so you basically just have to present the values of the input, and then you ask yourself, so can I track down how the device is going to act because of the input pattern being blah blah blah, and then I change one pin at a time, and I change one pin at a time. Can I explain using this particular process why the device is going to settle on a particular state? So that part you can kind of practice, and you can also verify the answer because Logisim can give you the final answer. Logisim cannot explain what happens in between the input pins being changed and the final state of the devices settled, but it can at least confirm the final state. So that would be one way to kind of practice this kind of question. Oh, okay. All right. Can I produce another sample of question number 3? Yeah, I can. So the only difference, between the variations is going to be the value, the constant. The value of v is changed, and I think in some of the questions I also changed the erroneous bias. But I have to think about the correct answer too, right? Because I have to be able to give you the actual correct answer if I give you a variation of this kind of question. I'm not really sure whether that's going to be helpful or not. I think if you are to go through the process to say, okay, let me give you some values that you can work with here. So I would start with something that's easy, like 1.125 as the actual value, and then you can just kind of multiply this by a power of 2. So you can say, okay, what about 1.125 times 16, right? Okay, 1.125 divided by 16. So these are potential values of v. Okay, so v being these specific value. So you want to basically be able to by hand convert these values into the 64-bit representation using the correct format of the double precision floating point numbers, because that part you can verify by yourself. Okay, because I already in the lecture I showed you guys a technique, a trick that I use in order to check whether my bit pattern does represent the value that I think it should be representing. So that part you can do it and verify for yourself. The erroneous part is a little bit trickier because that means you have to intentionally mess up the bits, right? And so that part to come up with your own key is going to be harder. So I can see that. I'll see if I can generate more variations of this, but it really is not about you know getting used to this specific process. You kind of have to break this process into the part where you figure out the sign bit, the part that you figure out the exponent. Because in order to figure out the exponent, you have to figure out the bias as well. Um, and then there is also the part about the fractional part of the mantissa. Okay, so given the fractional part of the mantissa, how do you come up with the mantissa itself? Okay, that's a very simple question to answer, but that's the kind of question that you want to be able to answer. So I'm not sure whether that's helping or not. In other words, it's the concept that counts, right? Every floating point number has three components: the sign, the unsigned number that is representing the biased exponent of 2, and then the fractional part of the mantissa. So you kind of have to understand what each term is, how to compute that, and how where does it belong to in the 64-bit of a double precision floating point number. So there are so those are the core concepts that you want to master. And once you master those concepts, the rest is just adapting what you already know to whatever the question is asking. So I hope that makes sense. I'll see what I can do with question number 3. The erroneous part is the part that is difficult, for you to kind of figure out whether you got it right or not. But the part where I give you a bit pattern and you figure out the value, that part should not be too bad. Yeah. Okay. Okay. So I can give you some exercises, some specific value or some specific bit patterns, so that you guys can go ahead and convert it one way or and the other way back. And obviously in this case, if I give you if I give you those things for practice, it obviously does not make any sense to use a tool online to do the conversion, because the whole idea is to make sure that you know how to do the conversion. So there's that. All right. So if there's nothing else, I can go ahead and sign off from the voice channel. I'll still be online, because some of you may want to do some studying right away and ask more questions. So I'll still be online to answer those questions, but I'm not going to give you a lab tonight, because I think this is enough intellectual stimulation already. Unless you guys really want something to do, then I can potentially give you something to do if you want. Alrighty. Doesn't look like there are any more questions. Oh, okay, here comes Connor. Okay, go ahead, Connor. Bet. Not quite sure what to make of that, but it's not in the form of a question. Oh, okay. Why is it? Why is bet the same as okay? Is it like you bet? No. All right. I bet you would. Okay, I see. All right. So I'm going to hang up from the voice channel, because I can give you an alternative, version of the test to work on. I think I have, the automated generated answers as well, but it's not going to be in the form that I talked about today. It's going to be in a slightly different format. So watch the text channel for the alternative questions. And all right. Alrighty, so I'm gonna sign off from the voice channel. I'll give you the alternative, another version of the same test. And also I'll include the key to it as well, so this way you know what the answer is supposed to be. Alright, cool. I'm gonna sign off from the voice channel, but I'll still be online if you guys have any questions.